So for those who are watching the recording, welcome to the debrief. We'll start by going over the problem cake transportation. So as a quick refresher on that problem, so there are two cakes, which are just shapes. So they could look like this could be one of them, and the other one could be this, for example. And you want to move one of the cakes upwards to the top and one of the cakes downwards. But you don't know which cake has to go up and which cake has to go down. So the question is, given a description of both the cakes, is it possible to slide either this one up and this one down, or the other way around? So can they freely slide up or down any distance without hitting each other? And so this problem was actually a bit of it seems complicated, but the solution is actually quite easy. Because if you think about it, the y coordinates don't actually matter. As you slide it upwards, all that matters is if you imagine you project these down onto like a line, all that matters is just their x coordinates. And if you draw a line based on where both cakes are located, the question becomes, do these two lines intersect or not? In this case, you can see these two lines don't intersect, which means we can freely move them up and down without hitting each other. But in the case that, for example, this is one cake here and the other cake is here, the first line will look like this and the second line like this, if you project both cakes downwards. In that case, the lines do intersect, and so it wouldn't be possible. And you can contrive other situations, but it resolves into, do these lines intersect? To find these lines, we can loop through all the points, and for each cake, we find the minimum and the maximum x coordinate, and then we have like minimum x1, like a minimum x2, and then maximum x1 and maximum x2. And to check if they intersect, there's a few ways of doing that, but one of them is you find the biggest minimum, so the maximum of the minimum 1, minimum 2, min x1, min x2. So this is like the minimum x coordinate of the two lines, and compare this to the minimum of the two maximums. And the idea is, if the bigger minimum, so in this case, that's here, if that occurs before the smallest of the maximums, so the less than equal to here, in that case, then they'll overlap. And if that isn't the case, then they won't overlap. There are other ways to check this involving a few if statements. So like the formula itself isn't too important. To get this, I recommend you just like draw out a few cases and work out something that works. Alternatively, you can have a few different if statements to check the different situations. But the main kind of detail in this problem is you want to turn all the shapes, just all you care about is the x coordinates, and then do they overlap or not? Does that make any sense? Or are there any questions about that? If there are, just put them in the chat. Secondly, I'll just get Wordle out the way as well. So there are quite a few requests for that. So in Wordle, so hopefully you know the rules of Wordle. If not, you can look them up. But the idea is you're given a sequence of guesses and the responses to them, and you want to work out which words could be the answer. In that case, how you do it is, again, there are a few ways of doing it, but what I recommend is first write a function that takes in, it takes in, say, your guess and what the answer might be. So you can pass it in a guess and an answer, and it will return the corresponding string. So like in this case, we have like G's, Y's, and dots. So you can write this function just by going through the cases. So you loop through the guess and you go, if the guess letter I is same as the answer letter I, you put a G for green there. If the guess letter I is in the answer but at a different spot, you put a Y, otherwise put a dot. And to return a string. Whatever language you use, you can do this in, whether that's C or Python, it will work. And then what you do, so you return a string, And then you loop through every possible answer. So you loop through all the words. And then for each word, you just assume it's the answer. And you run through every guess. And you go, if I pass in this answer with that guess into my function, do I get the same thing that I got in the input? So in the sample input, I can't remember what they gave you, but they gave you a word. I think the example wasn't the sample input, but the example had month and cloth. So if the question said, I queried month and I got back dot y dot gg or something, and you want to check is cloth the answer, what you would do is you'd pass month and cloth into your function. This function will return, in fact, it should return the same thing if I've worked it out correctly. And you go, okay, they're equal. That means cloth could be the answer. And you check this for everything. And yeah, that will get you Wordle. Okay. So again, if there's any questions, put them in the chat. Next up, I should have not stopped sharing my screen. We'll be back in a second. Next up, we'll be going over IMC Banner 3, and I'll hand over that question.
Cool. Hi, I'm Ryan, and I'll be doing this question. It's basically asking whether, so you have a string with a bunch of I, M, and C, and you're trying to fill in the blanks such that you have the most repetitions of IMC. So the IMCs don't have to be consecutive. In this example, if you have IMC, C, IM, IMC, that will count as 2. Because you have one at the start and one at the end. Next slide, please. Cool. So this is a greedy problem because our goal is to continue the pattern or to start the pattern. And it's always best to take whatever seems like the best option. So we can solve this using a few templates. Templates being like, if you see a certain situation, you want to fill in the blanks in a certain way. So obviously, if you see an I, an M, and then a space, you want to put a C there because that gets you one extra IMC. If there is a space and then an M, you want to put an I there because hopefully there is a C afterwards or a space. And if there is something else, there's no harm in putting an I. And similarly, if you see an I and a space, you might as well try to put an M and see how you go as you continue along the string. And if none of those are the case, that means you might be able to start a new IMC string. So you would put an I, and hopefully you have more spaces later on to put an M or to put a C. Could I get in the chat if that makes sense so far? Uh-oh. I'll go over the example and hopefully it'll make more sense. So for our sample case, we have an I and M and then a space. We can see from the templates that we want to use the first option and put in a C at that place. Yeah. And then as we continue, we get to the second blank and you notice that you can't continue a string. So we should start a new string of IMC. So we put an I there. And for the next one, we try to continue the string by putting an M. But at this point, we've run out of spaces, so we can't complete this IMC. And for the rest of them, the last 3 characters is already there, so you count that as another IMC. Nice. Okay, I hope that makes sense. Should we move on to robot vacuum 2?
Yeah, we'll do robot vacuum 2 next.
Nice. So for this question, we have a series of instructions. The instructions contain up, down, left, or right, which means that the robot moves in that direction. It moves one step, so you can think of it as a coordinate grid, and it's moving by x plus equals 1, or x minus equals 1, or y plus equals 1, or y minus equals 1. So it's basically taking unit steps around the coordinate grid. So what we have is that we can remove a series of commands. They don't have to be consecutive. And you want to do it such that the robot ends at the origin or ends where it starts. And you also want it to go the furthest possible before returning to the start. So in this situation, you can see the blanks is the places I've removed. And once you do that, you can move a distance of 3 before coming back to the start. It's a distance of 3 because if you look at the top right point, the coordinate is 2, 1. And so the distance is 2 plus 1. Okay, next slide, please. Cool. So our first condition is that we need to return to the origin. This means that if you move left, you have to move right again. And so the number of times you move left is also the number of times you move right. And similarly with up and down. So as long as this condition holds, you know that you're gonna return to the origin. The second condition is the maximum distance. So to maximize our distance, we want to go left as far as possible and then come back to the origin, or the other way around. If we have something like left, right, it's not as optimal as left, left, right, right. So what I'm getting at is you want a series of lefts followed by a series of rights. And similarly with ups and downs. So I guess with this in mind, does this make sense first? Can we have a yes or no in the chat? Is there a delay or am I just not explaining? Okay. I don't know.
People are saying yes in the chat. I don't know if you can see the chat, but yeah.
Yeah, okay, sure. I'll continue. So from this, we can get to our algorithm. So we want to consider every point, this point being an index. And this means that everywhere before you're going away from the origin, and everything after that, you're going back to the origin. So if you consider, so you want to consider each point as the furthest away point and count the number of lefts or the number of rights that you can count it so far. And this tells you the maximum distance you can get. If you're not familiar with Python, S # colon I means everything up to I, and # I colon means everything after I. So this is considering everything before and everything after. Yeah. And so you can see that you can calculate the maximum X distance you can get and the maximum Y distance you can get. And because your distance is the Manhattan distance, it's the sum of your X and Y distances. So yeah, that's the solution for this problem. I think I'm handing over to Isaiah.
Yes, so we're going to go straight to our last question on modern art. I will just go there and reshare my screen because there's a lot of demand to hear about that.
Yeah, while I was pulling that up, I think the solution for robot vacuum displayed on screen was n squared. So is that right? Or did I misread it? Whatever, I think it was n squared. Basically, yeah, for the robot vacuum one, to optimize it to order n. So in other words, so you don't have to have two kind of loops nested inside each other. That one didn't have two loops nested inside each other, but it had the splicing thing, accounting a splice of a list, which is order n. So it had an order n operation inside of a for loop. So the total thing was order n squared. But to optimize that, you just pre-compute like all the counts of lefts and rights, the prefixes and suffixes, which is a bit annoying, and it makes it a bit longer than simply what was shown on screen. But yeah, it's basically just pre-compute stuff instead of doing it slowly using the inbuilt Python splicing stuff.
Yeah, like when we get to mountains at the end, you'll see we use a similar trick to speed up that problem.
I guess I'm happy to briefly cover that question in chat. So if you want to go back to the slides, I guess I can have another go at explaining. So I think the important thing, I don't know if it was mentioned, but we consider like the first row is like the most important rule, and the second row is the next most important rule. So in particular, if we have something like that in chat, underscore ems underscore, then in the first case we'll put an I because the first rule that becomes applicable is just the bottom one. You put an I there. And then this one, you go down the list and see which ones might be applicable. This one's not applicable because you don't have an I, then an M. This one is applicable because your next thing's an M. So you put an I down. So it ends up working. And yeah, if you want to kind of motivate this, you see that these three are kind of obvious. They're just like continue the sequence if you can at all. And this one is the one that is specifically there to counter this case, basically. Because if you have an I and then something and then an M, the dumb thing would just to be try and finish off this thing with an IM. But yeah, you basically just have to add in that extra case, which is if you have an M next, then you should put an I straight away. Because there's no point putting an M if you're never going to finish it anyway. And in that case, you can actually get to that C at the end, which wouldn't be possible if you just put an M there, which is the slightly dumber thing. Yeah.
Your code would look like if the first case, else if the second case, else if the third case, else the fourth case.
Yep. And all of that just wrapped in a big for loop that just goes through in order. Yeah. Does that make sense? Great. Okay. So I don't know how many people managed to open this problem and understand what it was saying. It's actually quite a simple thing. It just happens to be an alternative task type. In particular, you don't actually submit a program, you submit just your output to what your program produces, assuming you actually write a program, which you don't technically have to, but I should explain the problem. So the problem is, you can ignore what I just said, but the problem is you have a grid of values and you're given another integer, in this case, n equals 10. And what you want to do is you want to select some of the cells in the grid. They're all from 0 to 9. So just so it looks nicer. And you want to select 10 of the numbers such that they're connected. So that just means that you can like walk from any one to any other without leaving that region. So like you can't replace that 4 there with a 5 because then that 5 would be disjoint from the rest of it. So that's the rules of the game. And the idea is, or the objective is to maximize the sum of the things that you select. So in this case, it's a 5 by 5 grid. And if you select those green cells, end up maximizing the sum. And it's not really important why, but solving this problem precisely, like finding the exact solution, happens to be NP hard. It's NP hard. So if the grid is big, in particular, in the problem, you're given a 100 by 100 grid. If it's big, then you can't find an optimal solution reasonably, essentially. So it happens that this one is basically just small enough such that you can find an optimal solution by doing a dumb brute force. Yeah, so what happened in the question is you're given an 100 by 100 grid, and what you do is instead of submitting a program, you just submit like which ones you select. So you just submit, for this problem, you submitted dots and like hashes, depending on which ones you selected. And so you just like indicate which cells you select, and then the website will check if it's a valid thing, and if so, it will give you a bunch of points dependent on the sum. If you just quickly close the slides and reopen them, I think I've updated to include the scoring function, in case anyone cares about it.
First need to refresh. Yep, the scoring function's there. I will reshare.
Yep. And also, yeah, in the problem, it happened that the grid that you were given, so you're just given one grid and you just submit your answer to that one grid. We could have put more cases, but we decided one case was enough. And all the values were randomly generated, and that's still, yeah, it's a problem that's still really hard to solve to any. It's hard to solve. It's basically impossible to solve optimally, but you can try and get close to a high sum. So in particular for this problem, it was a 100 by 100 grid. You know that the average is like 4.5. The average value is 4.5, and the highest conceivable thing that you can get is 9 times 1,000. So n was 1,000. So 4,500 you can just get by is the average thing if you just try random stuff, and 9,000 is the theoretical maximum. But for this problem, we found that 7,500 was something that was like hard to get to. In fact, we couldn't get to it, but we think it's very likely that you could get to it. I'll cover that a bit more later. But it is fairly easy to get close to it, or relatively easy to get close to it. So if you want to get to like 6,800, that's not too bad, and it ends up getting you, I don't know, maybe like 30 points for this problem according to that function there. So basically, as you get closer to 7,500, that exponential function will mean that you get more points. So like it accelerates as you get more points, and that happened to work for this question. And so the aim is to get really close to 7,500, and the closer you get, the more points you get. Okay. So yeah, for this problem, I don't have a solution, as you've probably gathered. So instead, I'll just cover a few ideas that can get you some partial points. And yeah, so it's kind of a dense slide. I just jotted down basically a lot of things that we tried and that can do pretty well. I guess the first one, which is really simple to understand and kind of funny, is you can just pick some random rectangle. So you have your 100 by 100 grid, and you just pick like a 10 by 100 subgrid of area 1,000. And this on average will get you 4,500 points because the average one's 4.5 and you pick 1,000. And that will get you 1% of the points just by that scoring function. That's a way to get 1% of the points. And I think quite a few teams did that. Maybe 10 teams or something did that. You can check the leaderboard. Okay, but the more interesting things, basically anything that is slightly smart can actually do pretty well. And that's why we did an exponential function, because anything that's slightly smart can do pretty well. So yeah, I'll try and speed it up so we can get onto some other problems later, but I'll quickly cover each point. So one thing that you might think of doing, this one, like basically anything that you think of doing has a good chance of getting like, I don't know, 40 points or more. And depending on how good an idea it is and how well you optimize it, etc., you can get pretty close to 90% or more. So yeah, this is a pretty simple strategy, which is to start from some node and just keep taking the biggest thing. You can do this in the implementation details. I didn't bother putting them down, but you can use priority queue, or if you don't know what that is, you can just do it naively, I guess. And because there's only one case and you can run it on your local computer, it can be really slow as long as it just prints something at the end. And so doing this obviously depends on exactly how you do it. Can get you around 40.5% of the points. Now, some better strategies are listed. So you can start from the full grid and remove the smallest thing. So it's kind of doing it the other way around. But you have to be careful so that you don't remove stuff so the graph gets disconnected, because the graph has to be connected at the end. Yeah, otherwise it would be a very easy problem if the graph didn't have to be connected at the end. So basically the nodes that you can remove without disconnecting the graph are called articulation nodes. And there's and they're very well. There's a very well-known algorithm to check whether they're articulation nodes. But you can also do it in many ways. But if you do that, it ends up being a bit better, and you get a bit more points. So without randomness, so if you just implement one thing, it'll get that amount of points. And if you add some randomness on top, and just keep running the same thing over and over again, then it actually has quite a high variance of around, I don't know what the variance exactly is, but it's enough such that if you just run it over and over again, there'll be enough variation such that you can get quite a significantly larger sum just by taking the best one. In that case, you get 74% of the points through this strategy, roughly. Yeah. So some other greedies, so instead of starting with the whole grid, you can say do the first one and then do a similar thing where you incrementally improve it by removing non-articulation nodes. You can't remove articulation nodes, so you remove the best non-articulation node. So the one that will increase your score the most by removing it, so the smallest one, and add the largest one that's not currently in your set, such that it remains connected. And doing some improvement things like this can get you to pretty good scores as well. Simulated annealing, you can look that up if you want, but I won't cover that now. Okay, so yeah. So yeah, I guess the rough idea is you can basically try anything and get a pretty good amount of points. I think in the contest, I think the highest amount of points anyone got was like 25%. It's probably because there's just like, it's very hard to do this problem when you have 12 other problems or so to approach. But yeah. So yeah, the best solution we had, got that, but we're confident that you can do a lot better. Yeah, like almost definitely you can get at least 100 more than that, probably more. And remember 7,500 was what you needed to get full marks, but we weren't expecting anyone to get full marks. Okay. So yeah, that's the strategy, not super important, but it involved basically some of the ideas above. It just happened, we didn't really know that it would be, I think, but it just happened to be the best. Right. Yeah, so that's probably it for this question. Are there any questions on it, or does anyone have their own strategies that work? I think, I don't know, not to put them on the spot, but I think the team that came first got a respectable amount of points, or at least more than most of the other teams. I think it was like 22% or something. I don't know, might be interesting to hear what their strategy was, because we don't know, because they just submitted a file that looked something like this. Yeah. Okay, I don't know if they're around or they're just typing it out, but we might see it later. But yeah, solutions can look something like this. They're not very interesting to look at. I mean, it's interesting to look at, but it doesn't really tell you anything about how you tackle the problem. Okay, I'm happy to move on.
Yep, so we'll go back to Firefly. That's a nice one. Can you clear your drawings? So in Firefly, you had endpoints, and the question is how many rectangles can be formed using these points as corners? The rectangles can be like rotated rectangles. So you see in this case, the answer is 2, the 2 rectangles you can see in the diagram. So when attacking this problem, in the bounds, I didn't put them here, but it's up to 1,000 points. And you could get up to 20 points, like n up to 20 gave you like 25%, I think. So for n up to 20, you could try all 4, like you just brute force n to the power of 4. So try every possible set of 4 points and then check whether they form the corners of a rectangle. That involves doing some maths. There are a few ways to do it. I won't go over the details, but use some like geometry, whether that's like trig, or I think you can just like apply Pythagoras' theorem, see if Pythagoras' theorem applies. That might also work for checking right angles. But there are a few ways of doing that. And just check whether the 4 points form a rectangle or not. And either just check if the corners are all right angles. And yeah, do some math to do that. But the full solution is quite a lot nicer. So to solve this, it's worth thinking about, well, what properties do rectangles have? And there's more than one solution, but what I'll present now is what I think, in my opinion, in our opinion, is probably the nicest of the solutions. So to form a rectangle, you can consider diagonals. So you have a rectangle, you have these two diagonals. And if you look at a rectangle, what properties do these diagonals have? Well, the first obvious one, I think, is that they're the same length. Oh, I spoiled the second point. The first point is to have the same length. To think about this, just maybe draw out a few cases. I'm not going to prove it formally. You could prove it by going, I think just these two are like going to be the same length. And these two are the same, or they're all four of them the same length. In fact, all four sides are the same length. And so the total diagonal is also the same length. But I'm not going to prove that formally. You may have done this in a math. You may have proved that in a math course at some point, but I think it's fairly obvious by looking at it and drawing a few cases that the two diagonals will be the same, even if you don't formally prove it. The second thing is they have the same midpoint. The midpoint is just this point here. Both diagonals share a midpoint where they intersect. And one question that may arise is it sufficient if you get two lines? You have one line here and a second line here. If they have the same length and the same midpoint, do they form a rectangle like this? And the answer is yes, they do. So to convince yourself why it is true, let's look at the first direction. First of all, if we have a rectangle, then these two conditions are definitely met. If we have these two conditions met, do we have a rectangle? The answer is yes. Again, you can prove it properly, but in the interest of time, the idea is if you draw out a few cases, you can convince yourself why it's true. And then if you want to prove it formally, I'll leave that up to you. But here's another example. Two lines that have the same length and share a midpoint, rectangle, etc. And based on the angle between the 2 points, if the points form a right angle like this, if the lines form right angle, we'll have a square. If the points like the angle is more like this, we'll have a very long rectangle. But it still forms a rectangle. So the idea is we consider every pair of points. So for each 2 points, assume they are diagonal. So pick a pair of points, calculate their length and their midpoint. So it's best to not use floating point numbers because you can have floating point errors. So to calculate their length, you can just use like Pythagoras' theorem, but don't square root it. So just go the difference in x squared plus the difference in y squared. So using Pythagoras, I'll give you the distance squared. Normally in problems, you want to avoid floating point numbers where possible. Because yes, if you've done 1521, you would have learned that floating point numbers are not exact. And so leave distances in distance squared if you can, they'll stay as integers. So calculate the length squared and also the midpoint. And if you double the midpoint, it'll always be an int as well, because it might have a 0.5 in it. If you get midpoint doubled, it'll be an int as well. So you have three numbers. You have the length squared, you have 2 times the x coordinate of the midpoint, and 2 times the x coordinate or the y coordinate of the x point of the midpoint. The times 2 again is just so they stay as integers. Otherwise, you might have a 0.5 in there, which is probably okay, but to be safe, avoid floats where possible. And then the idea is if 2 diagonals, so if 2 different pairs of points meet both these conditions, then you have a rectangle. And so you group pairs based on do they have the same triplet of numbers here? And let's say there are x diagonals that all have the same length and the same midpoint. This gives you x choose 2 equals this number of rectangles. So as an example, if you have like this diagonal, my drawings are bad, but imagine they all have the same length and they share a midpoint. Then in this case, we have 4 lines. This will give us 4 times 3 divided by 2 equals 6 different rectangles. This one, for example, will be one of them. So will this one, and there'll be a few other ones. And to calculate this, there's a few ways of doing it. One is you can calculate this number for each of the pairs, so all n squared pairs, sort them and use that to find equality. The other way is if you use something like, for example, a Python dictionary, or in C++, a map, for example, you map from these 3 numbers to a counter of how many triplets have that number. And you just have some way of counting for each grouping of 3 numbers, length, x coordinate of the midpoint, y coordinate of the midpoint. For each triplet of that, you check how many values have that, and you can use that to calculate the number of rectangles. And the speed of this, it's going to be either order n squared or n squared log n. Why is that? Well, there are n squared pairs of points. And then you want to count how many pairs of points have like the same 3 values. To do that, you can either use, so if you've done courses that cover this, if you use a Python dictionary or a C++ map or a different language's equivalent, in this case, it'll either be a hash map or like a binary search tree. That'll give you either this complexity or this complexity. If you're sorting, that's this complexity here to sort n squared numbers. And so you end up having one of these time complexities. But yeah, the main idea is you make these observations about what rectangles look like, and you use that to then count how many there are. Are there any questions about that? If not, I'll hand over to Isaiah to do Treetown.
Yep. Okay, so this problem is actually fairly simple to explain. It does involve a graph, but yeah, it's still simple to explain. So you're given a tree, and very briefly, it's like a collection of sites and roads such that they're all connected to each other, so you can reach one from any other, and also you can reach one from any other in exactly one way. So there's no like loops, basically. Okay, so you're given like all the edges, and you're also given a big number on each thing. So in this case, the big number is the thing that matters. The small one is just an index. So you can see it goes 0, 1, 2, 3, 4, 5, 0, 1, 2, 3, 4. So yeah, so you're given the shape of this thing as well as an integer on each node. And the question is not to find a sequence of nodes. It's actually to find the length of a sequence of nodes such that the first one is 0. So we have to start here. And each consecutive pair of nodes is adjacent in the tree, and each node appears. Okay, so I'll just do an example. So one sequence of nodes is to start at 0, and then go to node 3, then go to node 4, and go to node 3. I'm just going to do a fake sequence because I can't be bothered writing a long sequence. So let's chuck in a 1, a 3. So yeah, so you can see that each pair, they're adjacent. So you can go from 0 to 3, and then you go to 4, and then 3, and then 1, and then 3, and then 0. And you have to make sure that the number of times that each thing appears is the label in the tree. So 3 has to appear at least once. 4 has to appear at least twice. 1 has to appear at least once. And so this sequence isn't valid, but I think you get the point. And yeah, so the question is to find the length of the sequence, the shortest sequence that satisfies these 3 criteria. Okay. So in the question, you could get 50% of the points where the tree is quite simple. It's just a line like this, which is a case of a tree, probably one of the more, the trivial case of a tree. And yeah, so it's useful to think about this solution because it helps you get to the full solution, I think. So we're just ignoring the indices because they don't really matter. And we're trying to find how can we walk along this tree such that we visit each node the required amount of times. So I'll just draw out like what it would look like. So what you do in this case is you go here, then here, then here, then here, and back here. And then you'd go back a couple more times. That kind of makes sense. So why did we do that? Well, the first thing that we did was we went all the way to the end. And it's not obvious why you have to do that, but it's also true. So you should always go to the end. And the reason is if you stop somewhere here and you like, so I'm saying at the very beginning, you go from start to end by taking each node in order. And the reason that you should do that is because if you went back at this point, if say you went back here, then at some point there's stuff later on, right? Because every node is positive. So at some point you have to come back here. And so you might as well have delay this until later, because if you delay it until later, then you won't have like potentially wasted this stuff here. So if you had a case where it was like 2, 0, 2, 1, then clearly it would have been bad to go back here, because you have to come back here and you just wasted a lot of time over here. So which you might have had to waste it, but in this case you didn't have to waste it. So if you waste it, you might as well waste it. You might as well spend it as late as possible to minimize the possibility that you wasted. It's kind of it's a pretty informal argument, at least the way I've said it, but it is essentially just a greedy exchange argument if you've seen those before. But it is a little bit finicky in that you have to like exchange. You have to think about when you come back later and that you can swap stuff out. And it's never better to swap it out. It's never better to do it later in this case, or do it earlier in this case when you're going just from left to right. Okay, so the next thing that you do is as you're going across, as you're coming back, you just, whenever the thing on your right is not done, you just wiggle back and forth. So the first time that pops up in this case, so you go up to here, then you go back, then you check, is the thing on my right empty? And in this case, it's done because we already dropped it to 0 because we've already visited there once. So we just go back because there's no point going back there if it's already done. So we just go back to this one, and then we see this one's done as well because we've visited it twice already. So that's done. So we go back once more, and then this time, this one's only been visited twice. So it still has 3 left. So we have to go back at some point. And by a very similar idea, we should just go back as soon as we can. We shouldn't wait to go back, because if we wait to go back by going this way first, then eventually we'll have to come back here and do the same thing anyway. And that potentially wasted stuff down here. So yeah, again, the idea is we just take it. In this case, we take it as early as we can rather than coming back to it later. Yeah, I think the easiest way is just to play around with this case and see that it's just kind of obvious that you should never, or it's kind of obvious that it's never any better to do anything more complicated than just going to the right and then slowly working your way up, making sure you finish off every node. Okay, I think that's all for the line case. So the full solution is basically you just do the same thing, but on a tree. In particular, if you've seen a DFS before, instead of just going down to the bottom of the line, you do a depth first search so that you cover every node, and also so that you exhaust every node as you come back up the tree. So I can walk through it in this case. So if you start here, then it doesn't matter which way you go. And kind of the intuitive reason is because you can just switch them around at the end. You can switch them around if you went the wrong way. You can switch them around, so it doesn't matter which way you go. So we just go some random direction. So starting at 0, we go some random direction. And then so we only have one choice, so we go back up to 0. And now we just left this node and it's not done yet. So what we do is, so ignore this code for now. We just wiggle back and forth until we've exhausted this node. So just go back and forth between that and that. And now this node's done. Okay, so now we've finished this entire node. And so now we can move on to the next part of the tree, which is this part. So we go here, 3, and then we pick some direction to go to because there's still other branches. So we go down there, 1, and then we have to come back up, 3, and then we see, okay, we just left this node, but this one's done. We just went back up the tree, but this one's done. So we don't have to go back to it. And so we do this one, we see 4, but then we come back to 3, and then we see this one's not done yet. So we do it once more. Okay, and now we go back up the tree from 1, so we go back to 4, sorry, we go back to 0. And then we see that we've finished with that one because we've already visited it many times. if I haven't stuffed it up, this is the optimal solution, which requires 15 moves. So basically, we just do a depth first search over the tree, and whenever something's not finished, we just wiggle back and forth to finish it off. And you can kind of, so if you've seen a DFS before, then hopefully this will make a little bit of sense. If you haven't seen it, then I don't think there's much point explaining it in the interest of time. But yeah, you can see that we decrement X to say that we've gone to this node once, and we also decrement it on the way back. And so for each child, we DFS to it. And then if it hasn't been exhausted yet, then we wiggle back and forth the number of times that it needs to finish, the number of times remaining on it. And then we've also visited the parent node that many times. So we subtract that from that to say that we visited the parent node that many times. And yeah, this basically, if you just call DFS on the root, this basically ends up being enough. One small case that you have to consider is you have to make sure that you visit the root enough times. So if this root was like, instead of 4, it was like 40, then at the end, I think if you remember, the sequence had like 3 4s in it, or 4 4s in it or something, maybe 5. You can see how many it would be. Yeah, the original sequence had 5 zeros. So if you just do this, and it turns out that this code at least won't cover this thing 40 times. So at the very end, you should just make sure that the root, you go back and forth so that the root is also finished. And so you can just go to any node, it doesn't really matter. Okay. Hopefully that roughly made sense. Yeah, I think, yeah. Probably the best thing is to just look at this and see, to make sure that the answer is being updated at the right points, and the X values. So the X values are just how many times we still have to visit it. Just make sure that they're updating at the right points. Okay. That's it for this problem.
Okay. So we have, I think, mountain, which is the last problem remaining, unless I've missed one. So here we go. So mountains. So a quick description of the problem. There are n mountains, each with some height and some reward. So we've got the diagram from the sample case over here, where we have this one, we have mountain of height 5, of height 1, of height 4, and of height 3, with reward 1, 0, 1, 0 respectively. We have some more mountains and some more mountains. So the height is kind of anything from like 1 to 1 million, I think it was. And the reward will be -1, 0, or 1. So you perform a walk, and how this works is you start at some mountain. So let's consider this first example. We pick a mountain to start with. Let's say start this mountain here. We go onto it, and the cost of that is the height squared. So 1 squared is 1. It costs us 1 effort to get up onto this mountain. We can then walk to adjacent mountains. So we can walk left or right. If we walk left like this, that will cost us the difference in height squared. So difference in height squared is 4 squared plus 16 to go over here. Alternatively, to go here, it will cost us 9. And then we can keep going. We can go this way with a cost of 1. And then finally, when we're finished, we jump back down off the last mountain, and that costs us the height squared, so 9 here. So in total, the effort for the walk I described here is 20. And then the reward you get is the sum of the rewards. So in this case, the reward is 1. Notably, if you go onto a mountain twice, you only get the reward once. So if we were to go, for example, start here and kind of go back and forward a few times, then the reward from doing this would still only be 1. We wouldn't get extra reward from doing it many, many times. Okay, so the question is to find the least effort required to get a reward of at least 1. So you want to get at least 1 $1, I think was a unit in the question. We're gonna get at least $1, and you're lazy. What's the least effort required to get at least $1? So in each example, here it was 20. In this case, you want to jump on this -1, even though you get -$1, it's much cheaper to jump onto 5 into 6 because of the squared factor. You then go here and back again, and the overall reward you get will be one. It'll be -1 + 1 + 1. The effort required to do this will be 25 + 1. Do that 4 times, so 1, 2, 3, 4. So +1 + 1 + 1 + 1. Then 25 to get down again. It's a bit messy, but it costs you 54 in total. And that is the best way to get a total score of 1. You could just go straight up, straight down, but that would cost you 36 times 2, which is 72, which is more. Finally, in this last case, which is a middle case, the optimal solution is just jump up here and jump straight back down again for a cost of 2 squared times 2 equals 8. And the constraints are, in the full solution, is up to 100,000 different mountains. Now, you can get partial marks. I'm not going to discuss those in great detail. I'm going to go straight to the full solution. And there's an observation that you need to make in this problem, which is a bit counterintuitive, although once you think about it, you can justify it why. And I won't prove it until the end, but that is, there's always an optimal solution that starts and ends at the same point. So you want to go up to a mountain, walk around for a bit, and then jump off that same mountain. And that might seem a bit counterintuitive because remember in this case, if we go back a bit, here, in this first case, we started and ended at different mountains. But that's where this case is tricking you, because in fact, what you could do is jump up here, and then go back again. That will still cost you 20. Or you could go up here, and then back again. So draw this out in a bit more detail. So the 2 cases you could go instead is you could go up like that, up, down, down, or you could go up, down, down. Both of those start and end at the same point. Both of those get a reward of 1, and both of those cost the same amount of effort as all of the other cases. So it was just happened that in this example, there was a solution which didn't start and end at the same point, but there will always be a solution which starts and ends at the same point. And I'll prove that at the end, but for now, you're just going to have to believe me. And so using this observation, we can make a few different cases. So if we know we always start and end at the same point, there are only 4 possible cases. One of them is we go up and then straight back down again. The second case is we go up. We then go to the left some amount. So we go to the left, and then we retrace our steps and go back down again. The third possible case is the same thing, but we go right, like this. And the final case is we put those together. We go up, we go left, we come back, we go right, we come back, we go down. This was the third sample input case had this solution. No, second sample input case. So these are the 4 combinations. And if we have the observation that the optimal solution starts and ends at the same point, then these are the only 4 ways our solution can look like if you think about it. I won't prove that, but just if you have another case you think works, put it in the chat and I'll explain. Otherwise, any other case won't be optimal. Yeah.
Yeah, there's other ways to start and end at the same point, but they end up just doing some redundant stuff.
Yeah, exactly.
And that's
if you go up, left, right, left again. Like, why are you going left again? It's things like that. So we're going to consider just the walk left case for now. The other cases are all similar. Well, this first case is pretty easy to do. That's like, just check them all. This case we'll look at, the walk right case is the same as the walk left case. You just do the same thing, but in reverse. I'll explain the last case at the end. This is a little bit more tricky. But the idea is, if we want to walk left, we just keep walking left until our net reward is 1. So let's say, for example, we have values 0, -1, +1, +1. If we start here, we're going to keep walking until we have a net positive. That'll be here. There's no point going any further. We've already got a net positive. We're just going to return back to our start and finish and like leave. So what we're going to do, and if we were to start here, for example, then we want to go, this far, etc., etc. So for each point, we want to find the first part to the left, the closest thing to the left of us, which will give us a net positive reward. We then walk there, walk back, and we're done. Assuming we've decided where we're going to start. So we're going to try every possible starting point. Let's for now assume we've chosen one we're going to try. Then we just walk left until our reward is 1. We then turn around and come back. For the right case, it's the same thing. For this last case, ignore that for now. And so we can do this in order n squared already. To do it in order n squared, we just go for each starting point, just do a for loop backwards until we have a net positive reward, and then calculate using another for loop the cost of doing this. If you do this n squared solution, you can solve these two cases. And if you can find a way to solve this last case, which again, you can also do in order n squared. I guess I'll explain the last case now. The last case isn't that much different. The idea is the only time where you want to walk left and right is if you start on a -1. Because if you start on a -1, then it's possible you might walk left until your net reward is 0. So you find some values that sum to 0. And then you go to the right until you also have some values that sum to 0, like this. And if you put those together, then you might think 0 plus 0, but because it's -1 only gets counted once, it works out being a cost of 1 in total. So for example, if you have the case -1 plus 1 plus 1, then this here sums to 0. This sums to 0 as well. But the total thing sums to 1. And that's the only case. Why is that? Well, let's say you start on a 0 and you walk left for a bit and also right for a bit. Then one of these sides must have a net positive. So either this side here must sum to at least 1, or this side here must sum to at least 1. Otherwise, combined, they can't sum to 1. And if you're walking left and right, and one of the sides on its own is good enough, then why do the second side? You want to walk the least distance. So the only case where we want to walk both directions is where we start on a -1 and want to get to 0 on both sides. And so in that case, it looks very similar. We just walk left until our reward is, start on -1. We just walk left until our reward is 0. And we walk right until our reward is 0. And obviously the total reward will be 1 because of this double counting here. And in the same way, we can calculate the cost of doing that and give us an order n squared solution that will get us half of the points. But we want to do better than that. And so how do we improve our solution? Well, we first improve, how can we improve the part where we find for each mountain, how far left must we walk? So in this example, we have our reward values here. And I've also made a second array below it, which shows the sum of all the reward values. So this is 0. This is 0 plus 1. This is 0 plus 1 plus 1. So what we've done is, this value here, for example, is the sum of all of these values here. And why is this sum useful? Well, let's say we're starting way at the end here, and we want to know how far do we want to walk this way until we have a net positive. Well, my claim is, this is a 1 here, this is a 3 here. To get from a 3 to a 1, our number decreased, which means if you walk from here to here, we can get a total of -2. And that's true, we get -1 plus 1, -1, -1, -2. if we walk like from this one all the way to this one, then the net gain will be, well, it'll be 0 if we start, yeah, net gain from here to here will be 0. Or in fact, if this is a 1, that means the net gain from here to here is 0, to be exact. Because if this adds up all the values and this subtracts these values. So if this minus this is 0, that means the sum of all these values in here must be 0. So what we do is we want to find the first value that's smaller than our 1 here. That's this 0 here. This 0 is the first value that's smaller than our 1. And that means if this 1 here is the sum of everything. That's this sum. This 0 is this value here. Since this minus this is equal 1, that means the sum of all of these values in the middle equals, well, these values here equals 1. We can verify that if we want. We're not going to. But that means we've found a positive path. So for each point, we want to find the first thing before it that's smaller than it. So here, for example, this 2, if we start here, we're going to keep walking backwards until we hit this 1 or the thing after it. And that checks out. We have -1, 0, 1, 1, a net positive. If we start here, for example, we want to go back to the first thing smaller than it. That's a 2 here. So we go back to the thing in front of that 2, and we have a net gain of 1. If we start here, the thing before us is smaller than us, which means we're sufficient on our own. There are plenty more examples. If we start here, we want to go backwards to here, etc. So for each point, we just want to find the first value before it that's smaller than it. To do that, we do a for loop going from left to right. And for each value, we record the index where it last occurred. So let's say index 0, index 1, etc. We have an array and we say, okay, for each index, for each value, when did it last appear? Initially, that will be -1 to say that we haven't seen them yet. Then we get here and we say, okay, value 0 occurs at index 0. Mark that here. Value 1 occurs at index 1. And then we check, where was the last value 1 smaller than us? The last 0 was at position 0, which means we have to walk back to position 1, etc. We just put this as a 1 here. Oh, sorry, 2 here, index 3 here. Then we set this to index 3, to index 4. And then we look here. What was the last index that had a 2? That was index 2. That means we have to walk all the way back to index 2 plus 1 equals 3 in order to get a net positive, etc., etc. Let me know if that doesn't make sense. But this takes linear time to work out for each point, how far left must we walk? The next thing we want to calculate is, well, how much effort does it take to do that? To do this, we use another thing called a prefix sum, where the value here corresponds to the effort taken to walk from the start to that location. So for example, the effort taken to walk from the start to the start is 0. From start to here is 1 because of the 1 difference. From here to here, well, we add 4 because of 2 squared. So the total effort to go from the start to here is 5. Then we add 25 to get here, and then etc., etc. So to calculate the effort taken to walk, for example, from this 1 to this 6, well, this value here is the effort taken to walk from the start all the way to us. And then this 5 here is the effort taken to walk from the start to here. So if we go 44 minus 5, that will give us the effort taken to walk from here to here. This technique is called a prefix sum because we have a sum of the prefixes. And so we use that to quickly calculate the distance taken to walk from one place to another place. And so we use our first array to find out how far left we must walk, and then our second array to work out the effort to do that. And now we have an order n solution to calculate for each point, if we just walk left, how far left must we walk? We can reverse this and do the exact same solution for walking right. And in fact, our final case as well is the same thing. Because for this last case, we're going to work out how far left must we walk to get a sum of 0. And that's the same thing. We can use our same arrays to calculate that. And so our arrays, we can use them to, well, solve the problem. That's the solution, and it runs in order n. Let me know if that's confusing, because it is quite a difficult problem. But next up, the final thing is to prove this pretty bold claim I made, that you can always start and end at the same point. So I'm first going to not prove it properly, but give some intuition as to why it works. So remember before, we had the case where we had height 1, height 4, height 3, and that was it. And we had 0 plus 1, 0. And one optimal solution was to walk all the way across here, and it cost 20. But alternatively, we could have gone here, here, and then back down again. And that costs us also 20. Why does that work? Well, I'm going to prove for any solution where you start at a certain location, you walk for a bit and then finish, that it's always at least as good to return to the start. And why is that? Well, in any situation where you, so not this case here, let's consider any case now. Let's say we have 0, 0, -1, +1. I'm going to just make it a bit clearer. We have 0, -1, +1, +1, -1, +1, finished. So these are our locations. They're all different heights, but don't worry about that for now. And let's say we walk from here all the way to the end and back down again. Our total reward equals 1 if we add those numbers together. -1 + 1 + 1, take 1, +1 is 1. But let's say we start walking right and we turn around as soon as we have a positive reward. That's here. We've turned around at this point. And we go back again, like this. This might be better or it might be worse than doing the full run through. But now let's go from the other side. If we start at this side and then we walk left until our positive value, we stop here and then we go back. And notice how the middle point, the point in which they both had a positive value, this is the same point. And why does that work? Well, if we walk from the start all the way to here, and we have a value of +1, this means two things. First of all, there must be a +1 here. So we must have become positive and turned around. But also, the sum of all these values must be exactly 1, equals 1. But that means before, remember, we could walk all the way to the end and then finish, which means the sum of these values here must be 0. Because if it were all bigger than 0, it could be 1, but it must be at least 0. If it was smaller than 0, that meant our reward from going here would have been lost, which means this path here, this path here must have a sum of 1 as well, which means if we walk right until we first achieve a positive value and then turn around, that point must be before the point in which we do from the other side. They might be not equal. So if we consider the case where we have the values, let's say we have 0, -0, +1, -1, +1, like this. In that case, and then 0, in that case, the first point from the left we could have gone is to here, and from the right we would have gone to here and stopped. But the point still stands that we could do this and then walk back, and it would still work. It would still be a total sum of 1. And so the important point is there's one midpoint we can always pick, such that going from the left and going from the right both have a sum of 1. And why is that important? Well, the distance of, because it costs the same amount to walk forward as it does to walk backwards. Let's say the cost of walking to here is X, and the cost of walking to here is Y. Now, total cost of going from here to here will be X plus Y, including starting and finishing. But the total cost of going here and then turning around is 2 times X, and the total cost of going from here and going back is 2 times Y. And if X is less than Y, then 2X is smaller than X plus Y. And if Y is smaller than X, then 2Y is smaller than X plus Y. And if X equals Y, then 2X equals 2Y equals X plus Y. So in any of the cases, one of the solutions that involves turning around and going back will always be at least as good as going the whole way through. And so that proves that in this straight line case, that's never optimal. We can always, instead of going straight like this, we can go and turn around. The same applies if we walk the other way because it's symmetrical. Now, this doesn't prove it completely. There are still some other cases. We haven't proved, for example, that we don't want to do this. Walk up a bit. So we start somewhere. We walk left, we go back, we go right, and then we finish, for example. But this case can actually be proved in a similar way to the last case. I'm not going to go over all the details, but in general, I'll just give you the brief overview. In general, you can prove that any path will look like this. Start, go left some amount, maybe 0, come back, go right, go back, go down again. The reason why it looks like this and not, for example, like this, is that we never want to cross back over ourselves more than once. Like we never want to cross back 3 times. Because if we cross back 3 times, we might as well just remove the second time. So in general, any path will look like this. And you can prove that in this situation, you can always pick some midpoint similar to before and apply the same argument that I applied in that case, that either starting from here and going to here or starting from here and going here will always be better. And so using a similar proof to what I did, you can prove in the general case that it's always better to, it's always at least as good to start and end at the same point. But I'll leave that to details to you because it can get a bit messy. But if you draw out cases, I think it becomes fairly clear. I did write out the solution when I first came up with this problem, but writing it out properly is quite messy. Okay, so that's all for this problem. Let me know if there's any questions. If not, that's all for this debrief, unless anyone else has anything to say. If not, thanks for watching and thanks for doing the contest, and congrats to all of the winners.